So network flow, this is a very a nice topic that has both indirect applications. Many problems can be cast as network flow problems and then solved algorithmically, or the insights you get from those algorithms are useful mathematically also. But it's also a nice topic to illustrate different techniques in algorithm design and algorithm analysis, and it's got a wonderful history to it. Let me explain a little bit about what it is. So we have a network, or a directed graph. So here is one. V is there, T is here. So the edges in the graph are directed, and there's one designated node, which is the source, or S, and one designated node, which is the terminal, or T. And then there are other nodes, generally much bigger than just 4 nodes in here, or 2 more nodes. And in addition, every edge has a capacity. So in this little example, this is capacity 20, this is 30, 10, 20, and 10. So these are called capacities on the edge. And initially, you can think of this as a network describing pipes where some liquid is going to flow. I think that's the way people thought about it initially in the 1940s and 50s. Now you can think about these as just general channels in which some information can flow at a particular capacity, some time, at some rate. Okay, and what's going to happen if we think about liquid? I think that's the easiest. So some liquid is going to be available, continuously available at S, and continuously distributed or moved to T. And you can move instantaneously along this edge at most 20 units, along this one only 30 units, along this one only 10 units, and so on. So we're going to have it at some equilibrium after we start this thing, get the flow in there going. At some equilibrium, there'll be some continuous flow out of S and into T. And what we want to do is figure out how to route that flow to maximize the amount that goes from S to T. Okay, I'll be a little more formal about this in a minute. But the point I just want to make is that even though initially and intuitively this sounds like having to do with something, distributing liquid from S to T, and you may wonder how often you're going to have to do that, figure out how to distribute liquids. The actual formulation, this is a mathematical formulation, comes up in many different problems that have nothing whatsoever to do with transportation or liquids or even information distribution. There are many problems that can be nicely formulated in this way, even though they have nothing to do with physically moving anything. And we'll see some of those. So this is our basic problem, is figure out how to send flow along the particular edges in here, obeying the capacities, and then maximizing the amount of flow that goes from S to T. Now, I guess physically, if you just thought about flooding this thing and let the flow find its own way, that would work, except we're talking about doing this on a computer, and it's not a good idea to flood the computer, okay? My daughter just spilled Coke on her laptop, and that's not a good thing. Okay, so we don't want to mix computers and liquids physically, although you could, set this thing up. This is a complete digression. There was a nice little article years ago on physical devices for computing things. And for example, for shortest paths, you could set up your graph with string, and a string of a particular length that represented any particular edge in your graph. And if you wanted to know the shortest path from S to T, then you just pulled it, and whatever was the constraining path was the shortest one. So anyway, there are physical analogs you could set up, but we're talking about solving this problem inside a computer, so we have to figure out an actual algorithm to do it, not just flood from S to T and see what happens. Okay, so let me try to be a little more formal here. CE is called the capacity of edge E. Okay, so these are definitions. And it's going to be non-negative and, well, that's all we're saying about it right now. And then we have another number of interest, which is FE, and that's the flow on edge E. And it's constrained to be non-negative and less than the capacity of edge E. And I'm trying to follow the notation of the book, and I don't know why. Here they put E in parentheses, and here they put E as a subscript. It would have been much more natural to do both the same way, but at any rate. So I may slip up and put E in parentheses or something. I guess I see why they did it, because this would look then like, CCE, anyway, when you write it on a blackboard. But so that's, the flow of E is a number that's got to be between 0 and the capacity of E. And then a flow, F is a function which assigns a number, FE, to each E, and it's got to satisfy that. Of course, the flow number assigned to E has got to be between this range and this range. But it has other constraints. Well, actually, this is the first one, and this is called the capacity constraint. And the second one is the more interesting one, and that's for every node V, other than the source and the terminal node, or the terminal node is sometimes called the sink. But for every node V other than S and T, if you look at the values of all the edges that go into E into V, that has to be equal to the sum of the values where E goes out of V. And remember, the edges in this network are directed, so this idea of going into V or out of V is well defined. Okay? Does this look familiar to anybody? Anybody seen this in some other context? Yeah. Viruses going in and out? Or do you say wires? Wires? Okay, maybe. Nobody here is an electrical engineer?
What about conservation of energy?
Conservation of energy, okay, but in a slightly more narrow context. It's which one?
The current law.
Yeah, Kirchhoff's law. Okay, so another way of thinking about what's flowing along here is current. And the current law, Kirchhoff's law, at least without loss or friction or whatever it is, the current that goes into some node along the edges that touch the node has got to be equal to the current that leaves it. So this is called conservation, and it just means that whatever it is we're flowing, whether it's liquids or numbers, we're actually flowing here numbers, doesn't disappear. Nothing is gained, nothing is lost. Okay? So let's look at one over here. These are the capacities. So I could make an assignment of the flows on the edges. So maybe I put 15 here and 10 here, 5 here, okay, 3 here, and 8 here. Okay? And that should be a flow. Well, we see that every assignment on an edge, the F on the edge here, is less than or equal to its capacity, and it's a non-zero value. And we see 15 goes in, 10 goes out, 10 goes out that way, and 5 goes out that way for a total of 15. So 15 in, 15 out. And here we have 3 going in that way, 5 going in that way, total of 8, and 8 going out that way. So we've satisfied the capacity constraint, and we've satisfied the conservation constraint. And these were defined for, this is for every node other than S and T. And another thing to point out, if you look at the total flow that went out of S, it's 15 plus 3, which is 18. Okay? The total flow that goes into T is 10 plus 8, which is also 18. That's no coincidence. That's something we'll prove. And you can, if you think of this physically, if flow is going out of S and there's nothing coming back to S, I should have said that. In these networks that we're dealing with, it's assumed there's no edge into S, and it's assumed that there's no edge out of T. Okay, so let's put that down explicitly. No edge into S, and no edge or arc out of T. Okay? So again, if you think of this physically as some kind of liquid or current or information or whatever, current, I think I said that. Whatever goes out of S, it doesn't come back, and whatever reaches any particular node, however much goes in, goes out. Nothing disappears, nothing is gained, so where does it ultimately end up? It ends up here at T, and it better be the same amount that went out of S. At equilibrium. This thing is just flowing along, and whatever goes into S has to come out of T. Okay, well, actually, that's something we can actually prove in a minute. All right, so this is a definition. The flow, the value of the flow F is going to be equal to the summation of F of E out of S. Okay? And so this is the problem that we're interested in. So problem, find an assignment, or a flow. And when I say here assignment, it has to obey these two constraints, the conservation constraint and the capacity constraint. A flow F to maximize VF. Okay. So can we just look at this one over here? What is here I had a flow which sent 18. The total out of S was 18, and the total into T was 18. Is that the total? Is that the maximum possible? Or can you see a better way of doing it? Any suggestions?
You can route more to the HVT because you still have some capacity left.
Yeah, there's certainly, it looks like there's more capacity left this way anyway. So certainly you could bump this up by, yeah, it looks like the 12 here is the constraint. Even if we just went along this way, we could put 12 more that way, 12 more that way, and 12 more that way. So it's clear that what we have isn't the maximum. Okay, but what does look like the maximum? 30? Well, certainly you can't. Well, I'm jumping ahead, but it might be obvious to everybody that you can't do more than 30 because you have this constraint along here of only 20 out there and 10 out there. And in fact, I think it'll turn out that we'll be able to do 30 if we go 20 that way, 10 that way, 10, 10, and then 10 more that way and 10 more that way. Yeah, then we'll be able to do 30. So the 18 that we have right now certainly isn't maximum. And what we want to do is find an efficient algorithm. This is a class on algorithms, not really a class on water flow. But so we want to find an efficient algorithm that can find that assignment F, the flow F, that maximizes the value of the flow. All right. Another definition, and then we'll jump into an algorithm. F out of V is, well, that's just the E out of V. And F in of V is a similar thing, E into V. And then if we have some subset of the vertices, so capital V is the set of all the vertices. And if we have some subset of that, then we can also talk about F out of capital S. And that's just the summation of F out of V, where V is contained in capital S. And a similar thing for F in of S. Anyway, we can talk about what's into a set of nodes and what's out of a set of nodes. Okay, I'll write this out explicitly. V contained in S, F in of V. Okay, there's a distinction between little v and capital V, and there's also a distinction of whether V is in parentheses, that makes it a node, or V over here is outside the parentheses, that makes it a value. A little confusing, but I'm following the notation of the book. Okay, so Ford-Fulkerson, this was the first algorithm that was developed for finding a maximum flow, and this algorithm was, I think this was in the 1940s or 1950s, probably the 1950s, and this is what the book starts with. So it's chronologically where this field begins. So first, you just find an S to T directed path in the graph G. And so let's just do that on this example. We'll erase the flow values that we already had there. Okay, so we find some S to T path, maybe this one. Okay, so that's a path from S to T. And then we find what is the minimum capacity along there, in which case 20. All right, so actually I should call this 0 and 0 prime. 0 plus epsilon. Anyway, find the minimum capacity on the path, and then assign FE, minimum capacity, I'll call it B, for bottleneck. Yeah. The minimum capacity of the edges on the path. Okay, so the minimum capacity on the edges of the path, and then assign F of E equal to B for all E on the path. Okay? So just looking that over here, this is our path that we've found. Here's a capacity of 20, here's a capacity of 30, here's a capacity of 20. The minimum capacity on this path is 20. So the Ford-Fulkerson algorithm begins, this is why I label it as a 0, because it's really not the general step. It begins by assigning each edge to have a value equal to the minimum of what was on this, minimum of the capacities along this path. So the minimum of this capacity was denoted as a B over there. So, okay. So this is a flow. I mean, you should see that we've satisfied the capacity constraint, because we always were assigning the minimum that was along here. So certainly we're less than or equal to any of the capacities. And you should see that we've satisfied the conservation constraint because it's just a single path. So what's coming in is going out. Yeah, question?
So are you reassigning capacities to be the minimum along the path, or are you just making note of that and you're going to still remember the original capacities?
Well, I'm assigning F of V right now to be equal to B, and B is defined as the minimum capacity on that path. So I'm not changing capacities. Okay.
Flows. You're changing flows. Okay.
I'm assigning the flow value here. Okay. We'll change capacities in a minute, but we haven't so far. We haven't done anything like that. So this was just our initial assignment for f of this edge and f of this edge and f of that edge. Okay. Now, if you look at it, at this particular one, we're stuck in the sense of we now have a flow of value 20. And we might want to increase that. But with this initial assignment of 20 here, 20 here, 20 here, I certainly can't push any more along this edge. So in this network flow business, people use words like pushing or flowing along an edge, but it just means changing the assignment. Pushing more along this edge means increasing this value, this f value. And I can't do that because it's already equal to its capacity. I could increase this one, but then I'd be violating the conservation constraint because I couldn't put any more in here. If I try to increase this one, then I get stuck here because this edge out here is already equal to the most it can be, 20. And so it looks like, I mean, one might initially think that because I can't increase, at least I can't increase any of the values here by just increasing, you may think that this is the maximum. But this is a flow of 20. We already observed that we could flow 30. So just always trying to increase won't find the maximum total flow value. We have to try to undo some of the decisions that were made in this first path. And so now we get to the general step of the Ford-Fulkerson algorithm. This was just the way to begin it. Although after we see the general step, we could have actually started with a flow of 0 and then incorporated that as the general step. So we're going to need more than this space. So let me come over here. Hopefully everybody's absorbed these definitions. Okay, so this is the general step. And what it involves is building what's called a residual graph. GF, and that's given some flow F. So in general, we have a flow F, and over there we said how we can start with one. But I also observed, I just mentioned a minute ago that we could have started with a flow of 0, which is also a flow. Okay, but so you build a residual graph in the following way. For any edge E, for any E with the flow of E greater than 0. So if you have an edge where you've actually assigned the F value here to be something greater than 0, then I'm putting this backwards, but anyway. E is equal to UV. Okay, then you build, or you direct an edge from V to U with residual capacity. Am I beeping or somebody else beeping? With residual capacity equal to F of E. So this is what's called a backward edge. So you have an edge from U to V in the graph, and it has a flow which is non-zero. And then we're just going to put an edge directed in the opposite way with that capacity equal to the residual capacity equal to the F value. So here's U, here's V, and if we've assigned F of E on that edge in this way, so this is in G, then what we're going to do is have an edge that goes back in the opposite direction with the residual capacity C prime E equal to F of E. So this is the residual capacity, and I'll call that C prime E. I don't think they use a notation for residual capacity in the book, but I think it's useful to have something like that. Okay, so that's one case. And then, okay, hopefully everybody's remembered what conservation means. And then we'll put another type of edge in there, or other types of edges. For E equals UV with F of E less than or equal to capacity, or no, less than capacity of E. Put a forward edge from U to V, and its residual capacity of E is going to be equal to C of E minus F of E. So if we have presently in the flow, this is F of E, and it's strictly less than the capacity, it says, this is saying we have more capacity to push something in the forward direction. And the capacity of that, the residual capacity or extra capacity is C of E minus F of E. Right. So this is the total. Is there a question?
Do we have to have F of E is greater than 0 as we did in the first part, or is this for any F of E at all?
F of E is always this is a flow. So this is the assignment.
But in the first half here, this was for only non-zero flow having already been assigned.
Yeah, this is where something was already flowing here. And no, this one does not have that. So if you have, for example, an edge where there's a flow of 0 on it, its residual capacity is equal to its original capacity. Okay. So if we have a flow here on an edge from U to V, and its flow at the moment is 0, then the residual capacity is just going to be equal to its original capacity.
But the flow of E is always less than the capacity of E. So are we just doing this for every edge?
The flow of E is less than or equal to its capacity, yeah.
Okay, so this is just less than the capacity, I understand.
This one says less than its capacity, yeah. So if it's already at its capacity, then we're not going to put it. I mean, I could have had that in there as well, in which case this would have been equal to 0. Just saying the residual capacity in the forward direction is 0, and then there's nothing more that we can push in that direction. Yeah?
I'm a little confused about the residual capacity you were talking about on the reverse edge.
Okay.
How does that relate to the residual capacity on the forward edge?
Well, they're different edges.
Okay.
Okay. So the edges here are directed. So you have if the two ends are U and V, the edge is directed from U to V, or it's directed from V to U. You can have both. Okay. It is possible to have both a forward and a backward edge from between U and V. Right? So if you have some flow that's less than its capacity, some non-zero flow less than its capacity, you'll have some residual forward edge, but you'll also have a residual backward edge equal to that current flow. So you can have both. So this is what this builds what's called a residual graph. All right, and let's just let's look at the residual graph here. How am I going to do this? I don't want to clutter this up too much, so I'm going to try to U, V, T. Okay, so this flow is already at 20. Okay, so how much is its forward it's 0. So I'm not going to put an edge in there at all. Its capacity is 0. Its backward capacity, however, is 20, right? So I'm going to put that edge in there. This one is 20, so it has a backward capacity, a residual capacity of 20, and it has a forward residual capacity of 10, 30 minus 10. So you've got there a 10. This forward capacity is 0, but it has a backward capacity of 20. This one has a forward capacity of 10 and no backward capacity because there was no flow there at all. And similarly, this one has a forward of 10 but a backward of 0, so it's not even in there. So this was the original graph G, and this is GF, the residual graph, given this flow F. All right? So
If in the original graph we have a edge between U and S with some capacity, is it going to add it in the residual graph?
I'm sorry, what?
We have a edge from U to S. U to S.
U to where?
S. The source.
Oh, well, but in the original graph we didn't have one. But
No,
we,
if we have, then, if we have one, then is it going to be added with the reverse direction?
well, we've assumed that that in the original graph we don't have any edges into S, and we don't. That was what I erased down here, and we assumed we didn't have any edges out of T. Okay, does that answer your question? All right. So the assumption is in this original graph, there's no edge that goes into S. Okay. So and there's no edge going out of T. But I'm not sure if that answered your question.
What about V and U?
Z,
V and U.
D, and U. Oh, T and U.
No, I'm talking about V and U.
D.
V.
Okay, sorry. V and U. Well, there is one here. From V to U goes in the residual graph. It goes that way.
No, if we have like some capacity in the original graph.
Oh yeah, we could have had another edge going in the opposite direction, but in this example we didn't. Yeah, but it is possible.
Is it going to be added with 20 in the residual graph?
If we did have one like this originally, okay, we would simply treat these exactly under those rules. So this edge, if it had a positive flow in it, would then create a backward edge from it. And if it didn't, it would, well, if it didn't have flow up to its capacity, it'd have a forward edge that was the residual amount there. And if we had flow that way, then it would also create possibly a backward edge, but possibly a forward edge. And then after you did that, if you wanted to collapse those two that were in the same direction, you could do that if you wanted. But in this example, we don't have that coming up, but you can handle those as well. And in fact, you don't need to have the same capacity. I mean, you can have edges going in two different directions from the same pair of nodes, and they can have different capacities. That's certainly permissible. Okay, so this defined a residual graph, and what do we do with the residual graph? So here's where I say this was the general step. So you built the residual graph, and that's with that. Okay, and then let me give this a number. Number 1, number 2. Now you find an ST path in the residual graph, and let B be the minimum residual capacity on it. Minimum residual capacity on, let me give a name to the path, it's P. Okay? So over here, the algorithm tells us to find a path from S to T if one exists. Okay, I should have put that in there. It may not be one. And that will be our termination condition. But at any rate, in this example at this moment, we do have an S to T path. We can take this edge from S to V, and then go from V to U, and then U to T. Okay? So this is a nice little example because everything's forced. There are no choices in this residual graph. There's only one S to T path. And what's the minimum residual capacity on it? Or the minimum number along that path is 10. Okay? All right, so that was B that we found there. So we have the path P and we have the number B. All right. And we have all these definitions which we haven't even used, and I'm going to erase them already without even having used them. So this is still the general step of the Ford-Fulkerson algorithm. And now we're going to do what's called augment the flow F using the path P and that minimum capacity B. And it's just the following thing. F prime E is equal to F of E plus B if E is a forward edge in the path P. And F prime E is equal to F of E minus B if E is a backward edge in P. So let's look at this example again. So this was F. This is our assignment F. This is the residual graph G of F. Here we have a path P. And the rule is saying that we're going to come up with a new assignment F prime, which is related to F and also related to P. It's modified by the path P and by the value B, which is equal to 10. So according to this rule, now the flow here should be equal to what it was previously plus B. B is 10. What was it previously? It was 0. Okay, I didn't write a 0 there previously, but that was implied. So that's a 10. Now, the path here, this is a 10 because this is a forward edge. The path here has a backward edge. Okay, this edge is a backward edge, even though the path is going forward. Now, did I say find a directed path? Because that's find an S to T. Well, all these paths are directed. So we're not going to go opposite any of the directions in the residual graph. So, but this edge is defined as a backward edge. It was a backward edge. Every edge when you build a residual graph is either a forward edge or a backward edge. It's a well-defined notion. This is a backward edge. And so the rule says, now change the F that was assigned to this edge by decreasing it by B. Okay, B is 10. So this 20 becomes what? Well, it becomes 20 minus 10, which is equal to 10. Okay? And then the path P has this additional edge here, which is a forward edge. And so according to that rule, the F prime here should be a 10. So this is what F prime is. And if you look at this now, we have the F prime of any edge is less than or equal to its capacity, 20, 20, 10, 30, 10, 10, 20, 20, 10, 10. So we're within the capacities. Nothing's negative either. And do we still have conservation? We have 20 in, 10 going out here, 10 going out there, so we have that conservation. We have 10 coming in here, 10 coming in here, and 20 coming out there. So we have that conservation. And now if you look, we have 20 plus 10 coming out of S, and we have 20 plus 10 going into t. So we have another flow, which is f prime, and in fact, the value of that flow is now 30. Previously, it was 20. So we've increased the flow. So this is augment according to those rules. And now I want to put a this is going to be very interesting for people watching on TV. You iterate this process as long as you're able to find an ST flow in the residual graph. I guess to be absolutely formal here, because over there I'm talking about f's and here I'm talking about f primes, I better make f equal to f prime, okay, so that the program or the algorithm makes literal sense, because this is something we're doing to f. And I also need a termination condition. Find an ST-directed path in the residual graph, and that's if there is one. If there is one, else stop. So this algorithm iterates. Step 0 is the initiation, and this is the general step of the algorithm, which iterates until it stops. So we have a number of things we want to prove here. One is that as the algorithm is going along, we actually have a flow at every iteration. We'd like to prove that the algorithm terminates. We'd like to prove that when it terminates, we have a maximum flow. And then we would like to see what's the complexity of the algorithm. How fast is this algorithm? All right. So actually, let's just finish this example, because now that we have this flow, let's look at its residual graph. All right. So I'll erase this and do it again. So this was the flow f prime, but I've just declared that that's the new f. Okay. So the residual graph for that flow, I have a backward edge here of 20 as before. I have now a forward edge of 20 and a backward edge of 10. And here I have a backward edge of 10. Okay, but no forward edge because this is at capacity. Here we have a backward edge of 10, and here we have a backward edge of 20. So this was the residual graph for this flow, and the algorithm says find an ST path if there is one, a directed ST path. Well, there isn't one, because there's no edge in the residual graph that goes out of S. There's no longer a path from S to T in the residual graph, and so the algorithm says stop.